Good morning. My name is Paul Stecuik. I'm with Northeast Power Systems, and welcome to this EasyPower webinar. Today we're going to be talking about capacitor-assisted motor starting. We're going to start off with NEPSI's background, who we are, what we do, and then we're going to talk about the impact of large motors on power systems, and more specifically, we're going to talk about motor starting. We're going to get the typical mitigation options that are typically used to mitigate the power quality issues with starting large motors. And the two key products currently used in the marketplace are reduced voltage soft starts and the VFD drive starter. And we're also going to discuss NEPSI's actiVAR, which is basically a capacitor assisted motor start. We're going to look at the economic advantages of the actiVAR when compared to a VFD drive starter. And then we're going to finish the presentation discussing how we use EasyPower to design and predict the performance of the actiVAR in the areas of dynamic analysis and harmonic analysis. NEPSI was established in 1995 in Queensbury, New York, which is 3 hours north of New York City. Our key product offerings include the metal enclosed power capacitor banks and harmonic filter banks between 2.4 kV and 38 kV, maximum BIL of 200 kV. This is our primary product offering, represents about 90% of what NEPSI sells. We also have a new product called the actiVAR, which will be the topic of today's conversation. It's a thyristor switched harmonic filter bank offered between 2.4 kV and 13.8 kV. And then we also offer a host of services in the areas of harmonic analysis, power factor analysis, motor start analysis, startup commissioning, and maintenance services to support our products. So pictured here is a NEPSI metal enclosed harmonic filter system located at the Red Chris mine in British Columbia. It was rated 23 megavars, 24.9 kV, and it's 5-stage, all-inclusive harmonic filter system. This metal enclosed filter system comes with all switching, all protection, and all control, as noted here in this one-line diagram for that product offering. So it consists of C-high pass, notch, and standard high-pass filters. You can see that we have rollout breakers for switching the various branches of the filter system. This filter system also included an automatic control system for regulating power factor and controlling voltage distortion within the mine's process plant. Because this system comes fully assembled and ready for interconnection, it typically has a much shorter lead time when compared to open rack system. NEPSI handles all procurement, all design, and then also all testing and commissioning of this product at the mine site. Typically, it has a lead time that could be as short as 20 to 30% of that of an open rack filter system. And when comparing the total cost of this product and when compared to an open rack system, can come in at significantly less cost because of civil work and installation work. And with some sites being at remote locations, this cost savings can be significant. So for today's discussion, we're going to talk about the actiVAR. The actiVAR is a cost-effective alternative to VFD motor starters where speed or process control is not required. It is basically a capacitor-assisted motor start, but instead of using conventional switches or circuit breakers, we use thyristors or thyristor valves. The actiVAR is a fast local supply of reactive power. It can support voltage for large motor starts and also support voltage for flicker type applications, which include welder and induction furnace type applications. It can also take care of impact loading of large motors. Such applications might include dragline shovels or car crushers. And it can also take care of voltage dips that might take place due to loss of generation within a facility that has local generation. The actiVAR can help a customer meet inrush current limits or voltage sag limits that might be required for a large motor starting. So pictured here is a 5,000 horsepower motor connected to a 5 kV bus, and this is an across the line motor start application. This is just to review what happens during a motor start. So when a motor start occurs, the 5 kV breaker to the motor is closed. It results in a draw of reactive power through the system. In this case, the reactive power flow was 14 megavars. It's often the case that the reactive power requirements to a motor can be up to 4 to 6 times the nameplate rating of the motor. In this case, the flow of reactive power from the source to the motor results in a voltage drop of 17% at the point of common coupling, or the 34.5 kV bus feeding this facility. And the secondary was at 27%. So typically, electric utilities will limit the voltage sag at the point of common coupling to about 4%. In this case, the 17% exceeded the utility requirements, and this customer was forced to look for other mitigation options. So when the cross-the-line motor start does not work, typically the other two options that are considered are reduced voltage soft start and the VFD starter. The reduced voltage soft start is by far the most favorable option, as it is the most cost effective. A reduced voltage soft start has a cost of about $40,000, and therefore it is typically what is looked at when looking to mitigate voltage sags associated with a large motor start. The issue with the reduced voltage soft start is that it operates by reducing voltage to the motor. It's basically like a light dimmer. As you try to push the voltage further and further down to reduce inrush current, there becomes a break point where the motor will not start, and the system will still have a voltage sag that exceeds the utility limit. And in such cases, the design engineer is required to look at a VFD starter. Now, VFD starter is kind of a gold standard here. It always works. You can always produce full torque by the motor, because you can always get full torque from the motor. It reduces both voltage and frequency to the motor, and therefore it is able to achieve full torque while basically maintaining terminal voltage or nominal voltage at the motor. In this situation, we show a VFD sync bus and bypass breakers. So in this case, we have one VFD drive feeding two motors. Essentially, one motor is started, and once it's brought up to speed, the bypass breaker is closed and brought onto the customer bus, and then the second motor can be started. This is very typical for gas pipeline type stations where you have multiple motors that need to be started, and speed control is not required. The third option to the right here is the actiVAR. This is the product offering that we're talking about. It is a capacitor assisted motor start. In this situation, we've had 4 6 megavar cap banks that are thyristor switched to supply reactive power to these motors during starting. So you can see that this is a shunt connected device. We're connected straight to the customer bus. There is no interposing breakers, no additional breakers required. When the motor starts, the CT here will sense the reactive power flow, and these thyristors will gate on to conduct reactive power locally to the motors. In comparing these three technologies, we'll start with the reduced voltage soft start. The reduced voltage soft start has the advantage that it's a low-cost option. Typically, with a price tag of around $40,000 for a 5,000 horsepower motor, it is a low-cost option, and it's typically what is first looked at when looking at the mitigation options. It also has the advantage that provides a soft start to the load, a mechanical soft start to the load, because you can reduce voltage to the motor, reduce the torque, and therefore it starts the motor softly. One of the disadvantages, though, is that it may not meet the starting requirements, the starting torque requirements for the application. And one of the main reasons for that is that medium voltage motors in general have a low starting torque. For this typical speed torque curve for a medium voltage motor, you can see that the starting torque is around 0.7 at 1 per unit voltage. And this is at 1 per unit voltage this speed torque curve is drawn. So if the voltage is reduced to the motor, the starting torque will be that much less. And the starting torque to the motor varies by the inverse voltage squared. And therefore, for instance, if you have 1/2 the voltage to the motor, you're going to get 1/4 of the torque. And for that reason, the motor may not want to start. Self starts also produce harmonic currents. If I click on the slide, you can see here that depending upon the phase angle operation of the soft start, it can produce harmonic currents. The graph here shows the orange curve for the fifth harmonic. You can see as the phase angle of the soft start is varied between 0 and 1.4, that it will produce harmonic currents based upon its phase angle of operation. Throughout its operation, it could have a maximum fifth harmonic current of 5.5%, and that's 5.5% of the starting current at that point of operation. So it can be quite significant. We have seen that soft starts have an impact on applications where shunt power capacitor banks are used, as it can sometimes enter into system resonance and cause spurious fuse operation. So whenever applying soft starts in an environment where there are power factor correction capacitor banks, resonance should always be considered in those applications as a possible area of concern. In regard to the VFD starter, it is the gold standard, but it is also one of the more expensive options available for starting large motors. Typically, a VFD drive starter requires an E-house. It also requires N+1 additional motor starters for the application. It also requires sync transfer controls. This picture here shows the area in the blue is the extra hardware switchgear and sync transfer bus required for a VFD starter. This all has an associated cost with it. The sync transfers are typically custom controls, requires custom programming of PLCs. The commissioning process can be quite complicated. So it is a more costly option and a much more complex option when compared to a reduced voltage soft start option. It does have the advantage that it does and will meet utility voltage sag limits and inrush limits. You get a soft start option, which is also nice because you can reduce the voltage and the frequency of the motor and basically start at full torque and meet the utility and voltage sag limits. The actiVAR, or the capacitor assisted motor start, it comes in at a lower cost than the VFD starter, but at a much higher cost than the soft start. So it's definitely an option that should be considered. It can be sized such that the voltage sag to the motor is kept to within the limits dictated by the local utility. And it can be sized to meet the local utility requirements for both inrush current and voltage sag limits. It is by far the lowest cost option. When considering the actiVAR, it's nothing more than a shunt power capacitor bank. So in terms of maintenance, it's much simpler to maintain when compared to a VFD starter. It's a shunt connected device and therefore does not require any bypass breakers or bypass switches. It does not require an E-house because it's outdoor rated. The key disadvantage to the actiVAR is it does not have a soft start function. We are basically supporting the bus voltage to 1 per unit, and you're applying the motor as an across the line start, and therefore the motor gets full torque. Pictured here is the actiVAR assisted motor start, and it operates similar to this function. When the motor starts, the CT here senses reactive power flow through the system, and the thyristors located here will fire to energize those 4 6 megavar capacitor banks. So we're essentially supplying reactive power locally to support the voltage. And if you recall, we had a 17% voltage drop before. Now we're at a 4% voltage drop, which was the utility voltage sag limit set on this customer. So we're supplying VARs locally here rather than having utility supply the VARs, and therefore we reduce the voltage sag through the system. You can see here that we've increased the real power flow from before, and we significantly reduced the reactive power flow through the system. This slide here shows the performance of the actiVAR versus across the line start. At the 34.5 kV voltage level, the across the line start, the voltage drop was at 17%. We decreased that to 4%. This was equal to the electric utilities voltage sag limit during motor starting. We've also decreased the secondary voltage drop from 27% down to 6%. This equated to more real power flow to the motor. It went from 2.5 megawatts to 4.6 megawatts, which then equates to more torque for starting. And you can see here that the starting torque, this is times 10, so the starting torque went from 0.37 for across the line to 0.67 for the actiVAR assisted start or capacitor assisted start. Starting time, of course, would go down with the increased torque and increased power flow to the motor. It went from 9.1 seconds down to 3.7 seconds. So overall, the actiVAR or the capacitor assist start can provide near full torque to the motor and can virtually eliminate the voltage sag. In fact, we could increase the capacitor bank ratings here to a point where there'd be no voltage sag during starting. But since the limits are set at 4% for this utility, we size the actiVAR to limit that voltage drop to just 4%. And that saves in the cost of the actiVAR because it's a smaller piece of equipment. This slide here shows the performance of the actiVAR. You can see on the top here we have the system voltage. The nominal system voltage here is 4160 volt. At the starting point, the system voltage is around 4160 volts, and as the motor starts, there is a brief dip in voltage. At that point in time, the actiVAR will push phase on the thyristors, which will then push out the current and supply reactive power locally. And you can see during the starting period, the voltage will rise to a point where the reactive power will start to drop off here, and the actiVAR output current will start to stage off. You see 3 switching operations here. The first stage coming off, second stage coming off, third stage coming off. And this happens over a very over a short period of time. And that is one of the advantages of the actiVAR when you consider it in comparison to a conventionally switched capacitor start bank. Conventionally switched cap banks use breakers or switches. These are much slower in operation. And this period of time where the reactive power requirements for the motor are dropping off is a very short period of time, and it's very typical that during this off period of time, as the motor reactive power requirements are dropping off, a capacitive start that utilizes breakers or switches will get an overshooting voltage. Because the actiVAR can switch within one cycle, we tend to avoid that overshoot that can occur. The same thing can happen on the front end with a conventionally switched capacitor bank. During the initial starting period, the voltage sag can last up to 5 to 10 cycles because of the speed of a breaker or the speed of a switch. The actiVAR uses a special control algorithm such that it can be turned on within about 1.1 cycles max for the slowest phase from the period of the start, at the time where it starts. The other interesting thing about the actiVAR is that after the actiVAR operates and starts that first motor, it will sit ready for operation for the second motor. And there is no necessary 5-minute waiting period with a conventionally switched bank. When you use a conventionally switched bank with breakers and switches, once you open the capacitor bank breaker or the capacitor bank switches. You must wait 5 minutes for a discharge period before you can re-energize. In a thyristor controlled capacitor bank, there's diodes that are anti-parallel to the SCRs. The diodes keep the capacitor bank at a negative peak, and as such they can be turned on without that necessary 5-minute delay that you would see with a conventionally switched bank. So the actiVAR can also be used with a reduced voltage soft start. This slide shows that here where the soft start will start to operate and the actiVAR will supplement the soft start. This is particularly useful in the higher horsepower range, for example, even at 5,000 horsepower, 6,000, 7,000 horsepower, where soft start cannot perform the function and typically would force you into a VFD drive. In this situation, the actiVAR can be used to supplement the soft start. In addition to supplying reactive power for a soft start to help support the voltage, it will also help reduce the harmonic current during the starting period. So the advantages of this system are it has a lower overall cost when compared to a VFD start project. It extends the functional range of the horsepower range that the soft start can be used in. Typically, when you get to the 4,000 or 5,000 horsepower range, a soft starts no longer operate because the voltage is too low to the motor. You don't have sufficient torque to start. The actiVAR can be sized to help the soft start and extend that range further to higher horsepower ranges, and of course save money. In addition to save money, the actiVAR could also provide automatic redundancy for the system. So the actiVAR can be sized to start the motor and meet the voltage sag limits of the utility. So it would serve as a backup for the soft start, and we can also get that soft mechanical start that we discussed earlier with the soft start that the actiVAR cannot do alone. So when looking at the cost of a 4-motor VFD start system, which includes the sync transfer bus and the bypass breakers and the e-house, a typical cost spread over a 10-year period, which includes the installation costs as well as the operating and maintenance costs, we come up with a cost of about $1.7 million. If I were to compare that to a capacitive start or an actiVAR system, the cost is on the order of $841,000. So there's significant cost savings when looking at a capacitive start actiVAR system in comparison to a VFD start system. The actiVAR can also be used on a plant-wide basis. Here's an example of the actiVAR being used on a plant-wide basis. We have a DEEPCUT gas plant here, which consists of 7 soft starts. You have 4 here, plus 3 over here. So a total of 7 soft starts spread on 2 different buses. And we also have 2 VFD drives. Those VFD drives are set up to start 2 9,500 horsepower VFD starters. These will all be placed inside an e-house. The drives may require some cooling equipment, and there's of course the lead time issues that you commonly have with VFD drives. They tend to have longer lead times. If we were to look at an actiVAR solution in this case, the actiVAR solution, we would replace those 7 reduced voltage soft starts with just standard across the line starters. So there's a standard 4 cross line starters here, plus the 3 over here, and we would replace the 2 drives here also with the cross line starters and include 2 actiVAR systems. In this case, those motors were quite large, so the system, the actiVAR system, is actually 42 megavars each, so a quantity of 2 42 megavar actiVARs would be required. But these 2 actiVARs would accomplish what the 7 soft starts and 2 VFD drive starters accomplished with just 2 devices. We could also add tie breakers to the actiVARs here to provide redundancy. And looking at the possible cost savings here, for the A bus, we come up with a cost of $2.2 million versus the actiVAR cost of $1.3 million. So just for the A bus alone, there's a savings of $900,000 here. If you look at the total plant-wide solution, it was about a $1.75 million in plant savings. And the system in general is a much simpler system. We have 2 devices instead of 7 soft starts and 2 VFD drives. The capacitor assist motor starter, or the actiVAR as we call it, utilizes thyristor valves, and the picture here shows 3 thyristor valves. They're single phase devices. They're filled with oil, so they're cooled and insulated with oil. It's a maintenance free device. It can be regarded as a single phase solid state switch. Operates much the same way as a vacuum switch might operate, or a circuit breaker. Send a signal to turn on, send a signal to turn off. It has a sub-quarter cycle response time, but when you consider control time and sensing time, typically we're on the order of about 1.1 cycles for the slowest phase to turn on. And if something like this were to break, it's basically a replaceable item. We send it back to the factory for repair, and we send a new one. This is a maintenance-free item. It turns on, transient free, turns off, transient free, and does not produce any harmonics. Internally, this valve consists of SCRs in one direction, diodes in the other direction, and it's a 2-bushing device. We have voltage sensors on the inside in the form of voltage dividers for sensing voltage. We also have thermal sensors in here for sensing temperature. So it's a self-protected device. We have a 5-pin connector up on top for connection to the control. Here's a picture of a 24 megavar system that went to Brandywine Station in Pennsylvania. It consisted of 4 stages of 6 megavars. It was designed to assist with the starting of 2 5,000 horsepower induction motors at a pump station for a pipeline application. So the pieces are shipped on a flatbed truck and lifted by crane and put into place. Essentially connect the bus bars up, connect some control wiring up between the stages, and this system is ready for operation. And this is just an additional picture. The customer actually wanted a small closet area to store some spare parts. Here is another project we did with the system to assist with a 10,000 horsepower synchronous motor start. This is a 13.8 kV application, and it's 24 megavars again, but it's in 2 stages, 3 steps. In other words, there's an 8 megavar step and a 16 megavar step, and the actiVAR control will turn on both the 8 and 16, or just the 8 or just the 16, to meet the requirements for the substation. So this is a synchronous motor application. It's important to remember that synchronous motors start as induction motors. They actually use their internal squirrel cage and develop their torque from that squirrel cage, or in motor size or winding that forms part of the synchronous motor. Northeast Power Systems uses EasyPower to perform dynamic analysis to determine the performance of the actiVAR. I'm going to get into a case study in which we use the EasyPower to do harmonic analysis, because we are applying a capacitor bank during that starting period. So it's important that you do harmonic analysis to simulate what's going on for the on period. And then we also do a starting analysis in which we're using the dynamic analysis package, and we're coming up with a before and after type of report where we look at the and predict the voltage before the application of the actiVAR. In this case, we actually compare it to measurements that were taken on site during motor starting and compare that to our simulations to tweak our model and make sure it's correct. And then we apply the actiVAR to determine the performance and the required KVAR to meet the performance requirements for the project. So let me start EasyPower up, and we'll show you one of the projects that we have been involved with using the EasyPower software package. Here's a case study for an application of the actiVAR. Okay, so I want to review the one-line diagram real quick. We have an incoming swing bus here with a primary voltage of 138 kV, a secondary voltage of 4.16 kV. Transformer has an impedance of 7.5. It has a rating of 7.5 MVA with an 8.4% impedance. This is the actiVAR bus, or the capacitor assist bus. This could very well be conventionally switched capacitors or a thyristor switched base system. This is actually two 6 megavar steps. When we apply an actiVAR to the system, we actually utilize detuned filters, something between the 4th and 5th harmonic. So these two 5.73 megavar stages actually represent 6 megavars output at 4.16 kV, and these were tuned to the 4.7th harmonic. The customer's main bus, and this is a pump station for a water pipeline that has 4 very large motors, two 6100 horsepower motors. These are new motors, and two 4,000 horsepower motors. The 4,000 horsepower motors have some capacitors connected to the terminals for power factor correction, and these reactors actually just represent 40 microhenry reactors that are typical for capacitor bank application. They will not influence the reactive output of that capacitor in any way. In addition to that, there's also capacitors located on the terminals of the 6100 horsepower motors for the same purpose for power factor correction. So a total of 4 pumps at this pump station, two 6100 horsepower pumps, two 4,000 horsepower pumps. All of these are equipped with reduced voltage soft starts. So for that reason, we have a model over here that represents the worst case soft start harmonics. If I were to double click on that bus behind that harmonic load device, you can see that we have a fundamental current of 3527 and also some harmonic current percentages plugged in here. These are based upon the slide that I presented earlier, the worst case harmonics at each possible phase angle. And what we do is we're looking just to capture the worst case situation to make sure that during a soft start application that the soft starters will negatively react with these capacitors here, or for the case of an actiVAR start, won't negatively react with the actiVAR itself. So it's just like any other harmonic analysis. We account for the soft start harmonics here and look at how they respond to these capacitors here. So it's important that we make sure that there's no resonant conditions during the starting period that can result in fuse operation in these capacitors as well as those capacitors there. There are some other motors in this plant, but they're much smaller motors, some 450 horsepower motors over here. They're not considered, but those motors also have some capacitors, and we want to make sure that those capacitors do not result in any kind of resonant conditions either. So for some additional background, what was going on with this customer is it was an existing water pump station with two 4,000 horsepower pumps. These 4,000 horsepower pumps had no problem starting. They used some reduced voltage soft starts, and they had no problem starting. You can see here, based upon the symbol, that we do have these motors modeled as a dynamic load, and therefore they will perform dynamically during the dynamic analysis. These motors over here we have not modeled in the dynamic analysis package, and then also the 6,100 horsepower motors we have modeled in the dynamic analysis package. So what was going on is they purchased two 6,100 horsepower motors here. They equipped it with soft starts, and the customer was given constraints by the local utility as to what to maintain the primary and secondary voltages at, actually the primary voltage only, and the soft starts were installed for the purpose of limiting the voltage sag and inrush current to the customers, to the utilities limits. When they went to start this facility with those soft starts, they found that they could not start the 6,100 horsepower motors because the short circuit level at this 4160 volt bus was too low. There was actually, with the soft starts fully phased on, these motors here would not start. So the soft starts actually had no function here. With them fully phased on, the motors could not start. So the purpose of the actiVAR here was actually installed to support voltage to allow these motors to start, and that is the situation here. So we're going to do a dynamic simulation with the 6,100 horsepower motor here. We're going to have one 6,100 horsepower motor already in operation. The other two 4,000 horsepower motors are offline. We're going to do the first simulation with the actiVAR offline. So I enter into the stability program here. It splits the screen into two, and I've already written some script. And you can view this. I'm going to actually view the script here, but this is the script that we're going to run. It's a 6,100 horsepower, no start, no TSC in this situation. TSC being a thyristor switched capacitor bank. So in other words, we're going to start this 6,100 horsepower motor here with this one already operating. So if I were to go in here and just do a script edit, I want to show you what we have here. So it's a 6,100 horsepower start, no TSC. We do an edit on this, and all we're basically doing here is we're saying run to time 1 second, and close the switch to the motor. This is the switch for this motor right here, this location for that switch, for that motor, and then we run to time 20 seconds. Nothing else is being done in that script other than the closing of the motor switch or motor starter. So I run the simulation. No, I didn't get that. Sorry about that. It's a no TSC start. We want to run that script. Hit run. And you can see here, the first thing you can note is that the per unit voltage is 0.761 per unit, and that's because the motor did not start. It's in a locked rotor condition at this point. The graph over here shows what is going on. The top graph represents the system voltage, or the 4160 volt voltage, and it drops to roughly 0.71 to the top right screen. Here you can see the voltage is basically 0.76 out here. So the voltage drops to roughly 0.73. The next curve is the starting current of 3.4, and that's 3.4 per unit starting current for that motor. And you can see at the starting point that the motor will ramp up in speed, but it never exceeds 0.836 per unit. And bottom curve represents the electrical torque to the motor. So in this situation, the motor did not start. Another interesting thing to actually do with the stability program, and I find to be very useful in reports, is actually to step through the starting or the script step by step and watch what's going on. So I'm just going to hit a reset here, and instead of hitting run here where we get the full simulation, I want to step through, and at 1 second I kind of click through. At 1 second you can see the power flow. So we're at roughly 18 MVA of power to help start this motor, and at a 0.423 power factor you can actually go through and change the power factor, the power flow options here, and say, well, I want to look at kW and kVAR instead. And you can see that during starting of this motor, you get about 16.4 megavars, or 16,415 kVAR of flow, and that's resulting in this 0.73 voltage drop. And that's why this motor will not start. It's just simply, the voltage is simply too low to start this motor. That 0.73 per unit voltage represents about 49% of the torque to the motor, and with a relatively low starting torque to begin with, this motor fails to start. So now we're going to apply the TSC, or the actiVAR, the thyristor switch cap bank, whatever you might want to call it. In this case, I have a script already written. We have a 6100 horsepower start script with the TSC in operation. So I'm going to review the script first to show you what is going to be simulated, and then we'll run the simulation again to show you the results. So in this case, 6100 horsepower start with TSC. We're going to do an edit on that just to show you what is written in the script. 6100 horsepower start with TSC, edit, and you can see that we run to time 1 second again, and then we close the number 4 switch, which is what feeds this motor. We also close TSC stage 1 and TSC stage 2 switches here, and that represents these 2 switches here, which feed the actiVAR. So we're going to be switching on the 2 actiVAR stages to simulate the energization of the capacitors. And then we're going to run to time 4.25 seconds, and we're going to turn off stage 1. And then we're going to run to continue with the simulation, and then run to time 5.25 seconds, and turn open stage 2, and then run to time 10 seconds. Okay, so we'll proceed with the simulation here. Remember, we're going to pull this down, 6100 horsepower start with TSC. We hit run. And you can see here the voltage is now 0.97, which indicates that this motor is no longer in a locked rotor condition. If I were to step through as we have done before, instead of hitting run, we step through this simulation, 6100 horsepower with the TSC. You can see that this 12 megavar actiVAR is pushing out roughly 9.6 megavars. Remember, the voltage is reduced here, so the megavar output of this capacitor bank is also reduced. But this reflow of reactive power is helping support the voltage here at this main bus, and maintaining a 0.88 per unit voltage, which translates to more torque to the motor and allows this motor to start. And so we'll go back to the full simulation again, and I'm going to expand this screen. You can see at the instant that the motor starts, the voltage sags, and then as the voltage starts to recover, we turn off stage 1. Voltage starts to recover more, we turn off stage 2. And this is actually how the actiVAR will perform. Now, EasyPower does not have code written to simulate the opening or when to open these actiVAR stages. So essentially what I've done is I step through the analysis, and I find at what point in time does the voltage get to where I need it to get to, and then I do edit the script and open the TIC stages at that point in time. I've also used overvoltage relays and connected it or associated them with the switches here, and had those overvoltage relays trip the associated switch at the time where the voltage rises above 1.05 per unit, and then I time coordinate these overvoltage relays. I have found that the effort isn't worth the output, and it's easier just to step through the analysis similar to what we have done before. I can go back and do that. Oops. From a harmonic analysis standpoint, we of course are, as mentioned, worried about the harmonics produced by the soft starts. So if we go into harmonics mode, right now we have all the capacitors off here. We have these capacitors off here. We can turn this capacitor off here associated with that motor starter, and then we also have the actiVAR offline. So in this situation, it should be just a straight impedance as we have shown here, because there is no capacitance modeled. Therefore, it should be just a straight line impedance. And if we were to do a summation all, we'd say we were to simulate one of these soft starts starting. And like I said before, this is the worst case harmonic, so we actually have all of the harmonic currents associated with a soft start modeled at their maximum value. In reality, it will be less than this, but this is a starting point to determine where I might see problems. So in this situation, is during the start, we might see 8.1% distortion. Likely will be less than that, but as a starting point, that's what I would be looking at. So if I were to just say turn on one of the capacitors associated with one of the starts, I would have a 14.3% distortion. You can see here that there's 207 amps of harmonic current flow into this capacitor branch. That certainly could result in fuse operation, and therefore I would investigate further. I can continue to do this type of analysis, clicking on various combinations that might exist. For instance, I might have this motor running and be starting this motor. In that case, and typically the way soft starts are operated is the soft start is turned on, and then at a later point in time, once the motor is operational or at full speed, the capacitor is switched on. So the starting sequence would be motor starting through the soft start, and then the power factor correction capacitor being installed or being turned on once the motor is up and running. So this would represent a case where if this capacitor is on, it would represent a case where this motor was in fact starting, because you would already have one on. So we'd be in this scenario with this motor running, this capacitor on, we'd be starting this motor here. In that situation, we would see roughly 178 amps. So still a relatively significant amount of harmonic current flow into a capacitor, certainly worth looking into. If I double click the bus, you can see that now I have a resonant point down in the 9.7th range. The soft start is going to be putting out harmonic currents at the 5th, 7th, 11th, and 13th and 19th harmonics. So in this situation, we're at 9.6 here. If I was to scroll over to the 11th harmonic, you can see that at this point there is some magnification of voltage distortion at that point, but not too bad. We would carry that analysis through to include other scenarios. In this case, we could have these two motors running, and we would be starting this next motor, this one here, and have the same type of analysis. So we carry that through to make sure that there's no issues. In the end, what we recommended to this customer was that all of these capacitors be removed and that they use this actiVAR here. And the actiVAR is actually a detuned 4.2 tuned filter branch, So there, as such, it generally does not create a resonance issue. In fact, I can open these capacitor branches and simulate what would typically be going on if these were operational. You can see that the distortion has dropped to 2%. So this would represent a situation in which we're starting one of these motors. We have an RVSS in operation, and the actiVAR is in operation also. And you can see that during starting, the actiVAR actually will act to reduce voltage distortion and current distortion into the bank and into the system for that matter. So this just about completes our presentation of this webinar. And for additional information about actiVAR or NEPSI's other products, feel free to contact NEPSI. Our website is full of information, including product literature, guide form specifications, case studies. We have some calculators on that website, and we also have some filter design tools. I appreciate everyone's time in attending the webinar. Hope it was informative, and I'm going to be available for answering any questions that anybody might have regarding this presentation and what we do. Thank you.